Yo, 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 what's up? Welcome to video 2 of chapter 22 for the second part of the day. We've got half of 2 problems to look at on the day 3-1-2. So, welcome to, again, the video. I've got to repeat myself, keeping the theme of 2, so you're welcome 2 times now. I want to know whether snoring rates differ for those under and over 30 years old. The data are from a random sample of 1,010 adults. Notice we've got this theme of 2 occurring even again. You've got 10 and then another 10 following it, giving you 1,010. 2 sequences of 2 numbers back to back consecutively. How awesome. Surveyed in the year 2002. Again, more 2s. They're surveyed in this Sleep in America poll. Of these, 995 responded to the question about snoring, indicating whether or not they had snored. There you go, 2 responses for each person that you are interviewing. This is getting more and more climactic, at least a few nights a week in the past year. Split into 2 age categories. 6% of the 184 people under 30 snored, compared with 39% of the 2 to the third 1-1 in the other group. All right, so let's go ahead and talk about how we can do a hypothesis test, because all that 2 silliness aside, that's really what we want to do here. We want to know whether or not people over 30 snore at a same or different rate than people under 30. To do that, we're going to set up hypotheses here. We have 2 population proportions we're talking about. First population proportion is P sub young. We care about P sub young. What is the true population proportion for people under 30 in terms of snore rate? We also care about P sub old, the true population proportion of people over 30 who snore. That is exciting. You are ecstatic. I am ecstatic. Let's get going. Here are the hypotheses here. We are looking at a null hypothesis. We are going to assume that the snore rate for people over and under 30 does not differ one bit. So we would say that P sub young minus P sub old, just like when we set up confidence intervals, we can look at the difference between 2 proportions using the normal bell curve. And I should really pause right here for a second and draw your attention to the fact that when we do a confidence interval for a population proportion from a single sample proportion, or when we do a hypothesis test for a single sample proportion, the conditions to use the bell curve are exactly the same. In fact, we're using the bell curve in the exact same way we just, for the confidence interval, have sample data to draw from. For the hypothesis test, when we're doing that with a single proportion, we have population data to work with, but the bell curve works the same way, conditions are the same. So you shouldn't be surprised that after I set up my hypotheses, I'm going to check the exact same conditions to move forward with my hypothesis test when I do a hypothesis test for the difference between 2 proportions, as I would when I do a confidence interval for the difference between 2 proportions. Same exact setup. So null hypothesis. There's no difference in the proportion of snorers among young and old. Alternative hypothesis would be that there is some difference between young and old in terms of snore rate. That we are not taking a stab at whether or not we think young people snore less than old or old people snore less than young. We're just saying that maybe there's a difference, and we're going to build up a case to try and reject the null hypothesis. So there are your hypotheses. We're assuming there is no difference. So let's go ahead and check out the conditions here. We'll still do those in red. There's not a whole lot of new interesting stuff going on there. Conditions are that randomization, as you know. I'll be brief here. We are told that we collected data from a random sample of 1,010 U.S. adults in the year 2002. So, yes, we're told samples are random. Okay, so there's randomization, 10%. Really, we know that the 184 people under 30 and the 811 people over 30 are less than 10% of all the adults in the U.S. 184 less than 10% of all adults, or really all adults under 30. And also, what was the other number? 811, less than 10% of all adults over 30. Okay, so we've checked those off, no sweat. Again, conditions looking at exactly identical when we did confidence intervals. Independence. Each individual was polled individually through their telefono. Individually. So, results, independent, both between groups and between individuals. Groups, individuals. Can I spell? Individs, there we go. All right, independence we have at least met or checked off here. Success, failure. Okay, kind of an interesting thing happening going on with this. Notice that, or not notice, but think back to all the other times we checked success, failure. We said if you've got population information that you're working from as your known, then that's what you throw at your sample sizes to make sure you have at least 10 successes and at least 10 failures. And that's what we have right here. The null hypothesis, I didn't finish writing that out. My B. P young minus P old equal to 0. We're assuming there's no difference there. Whoops, kind of a big deal. The alternative hypothesis was that there was no difference. So we're going to assume that snore rate's the same among young and old. We're going to see if that's not the case. All right, well, notice now with the new and improved and corrected null hypothesis that we are saying that the snore rate between young and old is equal to 0 when you subtract the two. That is to say that they are the same. But the problem with that is that we're not saying what we think the snore rate is among young people under 30. We're not saying what we think the snore rate is among people over 30. So we don't really have population data to work with, even though that's what we're basing the hypothesis test upon, this null right here. So instead, to check successes and failures, you got to work with the samples. We got to do the next best thing. And we were told that we had 26 of 184 people under 30 snoring. So multiply that p hat for the young people, the 26%, times your n sub young, the sample size for the young people. That's equal to 48, certainly greater than 10. Multiply your Q hat for the young people, the percent of the people who aren't snoring, times your n sub young, your sample size for the young people, and you get 136. Again, certainly greater than 10. Okay, so we've not got the at least 10 successes, at least 10 failures for the young. Let's do in green for the old. We've got p hat sub old times n sub old. That is the snore rate among the old people we found from our proportion or from our sample times the sample size of the geezers. So we've got 318, which is certainly greater than 10, and q hat sub old times n sub old equal to 493, certainly greater than 10. All of those p hats, q hats coming again from what we had up here. We had a p hat for the old group of 39%. We had a p hat for the young group of 26%. The complements are the q's. All right, so all the conditions have been met. To move forward with the model, she's a good-looking model too. We've got the two-proportion z-test that we are using. All right, and again, the bell curve that we're using here, no different than the bell curve we use for confidence intervals. So we'll go ahead and write out the mechanics next in blue. We've got some interesting stuff going on here due to the problem that we actually don't know the true population proportion for snore rate among yold. Yes, that's the hyphenate or the abbreviated young and old category. We don't know the snore rate for the young people. We don't know the snore rate for the old people. So mechanics. All right, we got our bell curve. And this bell curve, just as it did for confidence intervals, this represents how differences between samples of these two different groups would behave. based upon how we set up the null hypothesis right here, if we took a sample of the same size from the young and from the old, this bell curve is going to tell us the likelihood it would fall in some certain area. All right, so this is a distribution of difference between samples, all from the same population of U.S. adults. So the expected, so it's explaining how p hat sub young minus p hat sub old behaves, the differences between those samples. The expected value of p hat sub young minus p hat sub old is equal to, well, the null hypothesis said that we are assuming there's no difference among the population proportions. So we expect to see no difference among our samples. We're going with the defendant's argument, and we're seeing that the defendant's argument explains the information we know from the sample. All right, so let's go ahead and find the standard error, standard deviation of p hat sub young minus p hat sub old. Okay, well, to do that, that means we're going to have to know square root of p hat sub young times q hat sub young over n sub young, the sample size of the young or group here, not organization, sample. And we need to know p hat sub old times q hat sub, or why am I putting hats? Q hat sub old. These hats should not be here. I'm sorry. Because we need, with it being standard deviation, we want population information all over n sub old. All right. Well, again, you're running into that problem that we ran into earlier. We don't know population proportion of the young people who are snoring. We don't know the population proportion of the old people who are snoring. So, again, just because the null hypothesis says, let's go ahead and assume there's no difference here, we don't know what these individual data values are. So we're running into a problem if we try to build off of the standard deviation. We'd like to, because we're talking from population information to sample information, but we can't do that. So instead, we've got to use the sample data to build standard error, because we don't know p sub young and p sub old. We don't know the true population proportions among the young and old. So we're going to say the following. We're going to say, okay, well, we've got to back up and do standard error instead. We need the p hat for the young with a p hat for the old. Now, one problem if we do this, we know that we've got a conflict here. Notice that the null hypothesis says the proportion of young and old people snoring does not differ. However, your sample data circling right here clearly has a disparity, a difference between snore rate for young and old people. That's a problem. If we're trying to go with the defendant's argument here, we can't truly use p hat sub young at 0.26, and we can't truly use p hat sub old at 0.39 when we build the standard error, because that conflicts with the defendant's argument that there is no difference between the two different proportions. So this is what we do. We're going to pool all the successes from the young and the old together. So let me show you what this looks like. We're going to say, we're going to find a p hat sub pool. P hat sub pool. And that's equal to the number of successes we saw from the older group. That's 811 times 0.39. Round to the nearest person. You can't split somebody in half or into any fraction. 318 people snored of the 811. Plus the number of people who snored among the young, the 0.26 times 184. Again, round to the nearest person. So we saw 318 successes among the old, 48 successes among the young. And we're dividing by the combined sample size of 811 plus 184. And again, yeah, so we're making up a new p hat. This is not a sample proportion of successes that we found from either of the groups, but we have to do this so we don't conflict the null hypothesis assumption that the groups don't differ. We're going to say, well, there was a single pooled success rate here, which divide this out and you get 0.3678. And we're going to plug that in right here. So our standard error, to get around the fact that p hat sub young and p hat sub old do differ. It was 0.26 for p hat sub young, p hat sub old was 0.39. We're going to say this is p hat pooled times q hat pooled all over the sample size for the young. So we're changing this and this from how we calculated the standard error when we were working with confidence intervals. Plus, we're going to repeat that. P hat sub pooled, Q hat sub pooled, all over n sub old. Sample size for the older group. So you're plugging in 0.3678 right here, and the complement of that for Q hat sub pooled over sample size for the young was 184. Add that to the same numerator divided by 811, sample size of the old, and you get a standard error of 0.0394. So let's fill out what the bell curve has so far. It's going to be a little tight. We'll do this in red so your eyes drawn to the right things here. At the center of the bell curve is a null hypothesis assumption that there is no difference among snore rate for young and old people. So that's 0. 0.0 is at the center of our bell curve. Look creepy. Looks like big eyes and tiny nose. Anyway, to the right, you've got 0.0394, one standard error away. To the left, you've got negative 0.0394. I want you to think with me real quick, because we wanted to see if there was any difference at all among these two proportions. That is, do the proportions differ from 0? This is a two-tail test we're going to conduct. We need to know where on this number line right here that I'm outlining in red, where on this number line is the difference between our samples, p hat sub young minus p hat sub old. So we need this piece as well. P hat sub young minus, p hat sub old is equal to, well, 0.26 minus 0.39 is negative 0.13. So the bell curve is saying we expect to see no difference in these sample proportions of successes. Let's get that saying there. We expect to see no difference in the sample proportions of successes. That's what the defendant's claiming to be true. But yeah, we do. We see a huge difference. We see a 13% difference way down here. There is your p hat sub young minus p hat sub old at 0.13. And the null or the alternative hypothesis was looking for any difference at all. So we're looking to the left of this, in addition to the right of the fence, the same distance away from the mean in the opposite direction. So we need a z-score here, and we are almost done. Our z-score, let's go back to blue for mechanics. Z-score is equal to the negative 0.13 that we found for the difference between our samples minus the 0% difference we expected to see between the samples divided by your standard error of 0.0394 comes out to be negative 3.33. So your p-value is equal to twice the probability, because you're doing a two-tail test, that you see a difference between two different samples to be negative 0.33 standard deviations away from the mean or less, which is equal to plug in the normal CDF from negative 1,000 to negative 3.33, and you're looking at twice 0.00043, so that's 0.00086, clearly less than 0.05. So conclusion here. I'm going to write this out concisely, but then try to break it down as to what this means. Due to a low p-value, we reject the null hypothesis in favor of the alternative hypothesis. Okay, so what does that mean? All right, so let's go ahead and look back once more at the problem. Let's summarize here real quick. This is the only hypothesis test problem I'm going to show you in video form. We assumed we wanted to answer the question. With the sample we took, we wanted to answer the question, is there truly a difference in snore rate among young and old people? And to get at the heart of that question, we had to assume there was not. We don't know that there is. We're trying to build a case that there is. So we're going to assume that people are people, that there's no difference between them, hence this heavy-handed blue arrow that you've got right over here, okay? And then from that, we check the conditions just as we had for confidence intervals in the past. We decided to use the two-proportion z-test. That's our model. We centered the bell curve on 0 because we expected no difference between snore rate. We found the standard error in this really fancy way that depended upon p-hat pooled for a couple of reasons. Again, we couldn't use standard deviation because we didn't truly know the true population proportion of snorers among young people. We didn't know the true population proportion of snorers among old people either. So instead, we wanted to use the sample data that we had. But we couldn't just use p-hat sub young and p-hat sub old because they were clearly different. They were clearly different. One was 26%, one was 39%. That meant that if we were to use those in calculating standard error right here, we would be breaking the defendant's assumption that there is no difference in the snore rates. So we had to instead come up with a new calculation here. I don't want to call it a new statistic, a new calculation. We pooled all the successes together, divided by the combined sample size, and got a consistent value we could use for both p-hat sub young and p-hat sub old in calculating the standard error. So again, we're not breaking the null hypothesis assumption. All right, we did that. We added those into the bell curve. We're looking for a two-tailed test here based upon the not equal to 0 that we set up for the alternative hypothesis. We calculated a z-score after we found the difference between our samples. That's what we needed to know. It lies somewhere on that number line that is directly below the bell curve. We found it to be, oh man, a little sloppy. We found it to be negative 0.13. Get your z-score. P-value obviously is twice the probability that you have a z-score be that low or lower because you're looking at a two-tailed test, and then our conclusion. So we reject the idea that there is no difference in snore rate among young and old people in favor of the alternative hypothesis that there is a difference due to an incredibly crazy p-value. All right, that's your video. Have a good Wednesday/Thursday, and I'll see you.